The port of Rotterdam sits at the end of one of the big European rivers, the Rhine, and receives a lot of sediment which is deposited in the harbour. At the same time, from the sea also large amounts of material are brought in. Of course, to operate a harbour you need to maintain deep waterways.
We need to remove the sediment to keep the port functional. The best option would be if we could make something usable out of that sediment.
We're at the Royal Netherlands Institute for Sea Research on the island of Texel. Here at NIOZ we focus a lot on the composition, the properties of that material from the port of Rotterdam. This is vast amounts of material that has an environmental impact. It is quite high in organic matter, and when this organic matter is decomposed, CO2 is released. And see that surface layer? It's been in contact with oxygen and changed completely, different color, different appearance.
Very interesting.
Would be good also to measure how quickly the carbon is released from these sediments.
Yeah, absolutely.
It's time to get those to the lab.
Yeah. We took sediment samples from Rotterdam. Basically, we want to analyze the sediment at different depths. Now I'm purging the glove bag with nitrogen to avoid oxygen contamination in your sediment. I'm gonna do the first slicing. I am scooping up the first layer. At the very top few millimeter, a lot of reactions are happening. So you really want to do this very carefully. We later gonna analyze both liquid phase and solid phase. It will help us to understand the environmental impact of dredging or reapplication of this type of material.
In this project, we convert a problem into an opportunity. Our idea now is to combine the sediment that can release CO2 together with natural minerals that can absorb CO2 and use it as an actual building material. The natural mineral that can absorb CO2 that we focus on in the project is called olivine.
Hi,
We're in the laboratories of the Geoscience faculty of Utrecht University. And our responsibility is to look at how olivine and olivine amendments are going to actually react with seawater and with the sediment to try and get rid of CO2. Olivine is a very common silicate mineral. We find it in the part of the earth that's just underneath the crust. And what we want to do is chemically break down the olivine and create new materials when it reacts with seawater to add them to sediments and build new building materials.
So we want to determine an optimal ratio of olivine and harbour sediment that can sequester CO2 efficiently, but also that is environmentally safe as well. So now the mixture is done. So we are going to react this mixture at a temperature of 13 degrees Celsius, which is roughly the temperature of the North Sea. And this will be done in our climate chamber.
So the reaction that we want to happen on the seafloor is that we have acidity in the seawater, and this attacks the olivine crystal and starts to break it down. When the olivine breaks down, it releases magnesium, iron, and silicon. Because we use up acidity in the seawater, we change the balance between CO2 in the atmosphere and dissolved forms of carbon, like the bicarbonate ion. And this causes the system to actually draw down CO2 in the atmosphere and make more of this bicarbonate molecule. And the silica that we form can be part of the binders for the new building materials that we're creating.
What we are investigating now is what type of building material can this be. And one avenue is literally a building block, where together with Netix, an engineering company, we press building blocks of these mixtures for infrastructure. So for instance, we could have these blocks as part of coastal protection. At the same time, these mixtures can also be used in, for instance, ecological engineering. So you don't press it together, but you can maybe build islands that have a sediment that's quite good at absorbing CO2.
Or in theory, we could also mix the olivine into the sediment, into the normal disposal sites, and there it would incorporate CO2 from the sediment or in the natural environment there. The olivine can also help to absorb the toxic metals that can be released naturally from contaminated sediment. The iron is oxidized and becomes iron oxides, and these are really effective scavengers for heavy metals and remove them from the environment.
Some of these iron oxide minerals are magnetic, and the apparatus you see here is a magnetic separator. So I am trying to physically separate these iron oxide minerals with this technique. We also do solid analysis, and this type of information is very important if you want to put olivine and harbour sediment in the field. So we want to know what type of minerals will form.
I really enjoy using my chemical knowledge to find new solutions to problems that we're encountering, and maybe future problems that we're not yet expecting.
One of the big problems we have with communicating our science is that we often have bad news. And it's very difficult, I think, to reach people if you only have an alarming message. What I really like about this project is that we are trying to think about solutions to maybe combat some of the issues that we as humans have created.